Okay, so we're going to talk here about a collaboration between Quantinuum and BMW, and basically how that's working. But perhaps I could start by asking you, Robert, how did this collaboration come about? What's the history here?
Well, at BMW we have technology scouts, and they put quantum computing on our radar in 2017, and it very early on turned out that the hydrogen fuel cell is actually a very good pilot project to use quantum computing. Why? Because the fuel cell is expensive, there's a lot of platinum in it, and we don't really understand what the platinum really is doing. And quantum computing is close to chemistry, which is quantum physics. And so that seemed like a good starter. And then we looked around for companies who do quantum computing and know about quantum chemistry. And very soon we met CQC at the time and Quantinuum. That was in 2019 and 21.
And what's your side of the story, Elias?
Yeah, completely different. Well, first of all, thank you for The Economist, and thank you for everybody in the room. Lots of friends and people that have been on this journey for 8, 9, 10 years. So it's fantastic to be back, and this really has become the event. So well done to The Economist. I remember coming to the first one. So BMW are one of a very small handful of companies around the world, literally around the world, that have been pump priming quantum applications for a very long time. And without their involvement and companies like this, and frankly, I think there's only 2 or 3 others, we wouldn't be where we are today. So they extended the first collaboration, which was years away from seeing anything. And I remember seeing a venture capitalist. That was not deliberate.
Right.
That was not deliberate.
Okay.
Who's like, yeah, so what are you guys wasting your time with doing these things? Well, and the fact of the matter is, we have benefited because being inside an industrial organization, looking at the way that research funding is allocated, how decisions are made, and what happens once you get to certain tipping points, has actually benefited to making us who we are today. We are, of course, the world's leading quantum computing company, and that milestone in terms of our ability to understand how large organizations work is critical. Yeah, so I was at the Blue Yard event at Munich in 2017. I don't know if anybody else was there in this room. And that was, there must be somebody here. And that was a tipping point. BMW was there, Google, etc. So that's how we first met. Our first collaboration was 2018. I think 2021 was when we got involved in looking at a roadmap. And then last year, we decided that somewhere between 50 and 100 logical qubits in combination with some AI or classical supercompute cluster would make a difference. So.
Great. Well, so however you remember the history, or you've been working together for some time. So, what exactly is it still the hydrogen fuel cell? Is that still the focus of your work, or what exactly are you using this for now? And how has your use of this technology evolved? Back to you.
So it's actually broadened quite a bit. So we have, I would say, dozens of use cases, more or less precise, but some are very specific. And let me just name 3 of them. So one is the field of quantum computing in quantum chemistry. So the hydrogen fuel cell is one. Already last year, we did a very well-received joint publication also with Airbus in this field, where we analyzed with quantum computers what's really that chemical reaction at the platinum and how to improve on it. And we made a roadmap into what to do and how to employ quantum computers. And it's actually bringing about ways how we spend a lot less on platinum and how to even increase the efficiency of the fuel cell. And given that success, we also decided we'll do joint research into the lithium-ion battery, which we all know is basically in many of our devices and also in electric vehicles. So the economic potential is clearly visible. And so that's the first field, quantum chemistry. Then the second field is like where we still have challenges in high performance computing in simulations, like in aerodynamics. So we still have wind channels where we test vehicles, right? And it's an iterative process. And we see also a roadmap in quantum computing how this can be improved on. And the third area is multiphysics simulations. And today, when we do aerodynamics, we design a vehicle, then we measure, the drag, and then we go back to design. And this is an iterative process. And we see, early ideas on how to bring that together and do it simultaneously in a quantum computer. So to optimize the design and the airflow at the same time. And that obviously has huge potentials in getting to the right solution directly and being there much faster. So there are many more ideas we have, and that's.
But just to pin you down to this, are you essentially exploring what might be useful in the future, or are you getting useful results out of these systems now?
So for the fuel cell, these are results that we didn't have before. There are ways in how you could have generated that also with high performance computing if you knew what you were doing, right? But there we are spearheading and seeing results now. So we wouldn't know what we know, what's in that paper if we didn't have quantum computing. But you're right, we are still in an exploratory phase where we need great quantum computers to do good progress so we can really exploit the properties of quantum computers now.
Ilias, what's your take on this?
So I think that the broad generality of what we do as a firm is obviously across many different fields. But as far as BMW is concerned, there are some pretty foundational issues that we're looking at that will affect pretty much what we do elsewhere. So I would summarize by saying that the tipping point is now because we have computers that can't be simulated in certain areas. So if you've been in the field for 8 to 9 years, this is the point we've been waiting for. So that was literally announced yesterday, and it is now a reality. And so we can do things which cannot be done. The other thing is, in the paper that we did yesterday, although it wasn't with these guys, we established that we do things 30,000 times more effectively in terms of energy for the same computational aspect. And that matters because cost matters. Coming to the application, I'll say that anything that revolves around partial differential equations, so more broadly, so anything that requires that aspect, that boundary suddenly shifted yesterday. So when you can start doing hundreds of thousands of computations, you suddenly are starting to look at actual acceleration, because if you were going to do this using classical supercompute, let's say you have 3 years or 2 years in your math, well, suddenly now you're doing it earlier. And the last point I would make, because obviously this you could dive down this rabbit hole forever. Coming back to BMW, I think the nice thing here is that we have now become specific. We now have a timeline. We've now got an agreement on what the resource allocation is. Mm-hmm. And the bonus for us is when we sat down and agreed with Robert and Elvira and the team what our timeline was, we thought we'd get to a certain qubit count as measured by logical qubits with various error rates. I won't say what they are because that's subject to an agreement with BMW, but we had a 2027 timeline. Well, guess what? We've just doubled it. And that's not because we're smart people, whatever. It's because when you're suddenly looking at these boundaries, you learn more. And things like error correcting techniques suddenly become state of the art. So that's the bonus of doing this. So if somebody now tries to jump in, guess what? There's only one bloody machine and all the subscriptions are taken up. So if you think NVIDIA is in shortage in another year or two, but these guys are at the start of the queue. So I think there is a virtuous circle.
Right. That's interesting because so you learn how to use this technology and you're learning how to cooperate with industrial partners. I know analysts like talking about companies that are GPU rich. But we're going to have to start thinking about who's QPU rich, really, here, it sounds like. I was going to ask that next question, which is how these new, very impressive results that we've had from Continuum affect how things are going forward. You've alluded to that a bit there, which is you've got this agreement. What does can you give us a bit of detail on specific application areas where you're expecting to apply that and what that roadmap looks like? I realise that you won't be able to be completely candid, but can you give us some sense of how these new results have changed your outlook?
Well, the journey that we've been on to prove quantum supremacy, which is the phraseology that none of us like, but it was established by others. I mean, it's fine. I mean, it is what it is. You don't have to agree that it's going to be supremacy forever, but there's a terminology that is technical, so it's computationally provable or not. I mean, that whole sort of benchmarking system, I think, changes a lot. And we've obviously been on this journey with a handful of priority clients. We only have a small number of machines. And so therefore, we've allocated resources with A, people who matter, and B, problems that matter. So for us, computational biology is enormously important. And our partnership in Singapore is very important. Amgen is a shareholder of our company, so we have a partnership with them in computational biology. So that's one sector. And I wouldn't even say sector, that changes humanity, right? I mean, that is what we all aspire to. Carbon sequestration is very, 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 very important for us. We established IP there, which can now be moved into some sort of revenue sharing system because we can think about manufacturing those processes. There's a paper out there with Total.
So this is for direct air capture?
Yes, it's using these things called metallic organic frameworks. And we have two experts in the room who can actually tell you what that means. Yeah. But yes, short answer.
Right, great.
Short answer, yes. So Elvira's nodding. She was at Total then. And I think Simon's in the room as well. The third area, of course, which is capturing a lot of attention, is optimization in a financial context. And so we have a number of premium partnerships there. But the most important one that we can talk about publicly is with JP Morgan. Then we're fascinated by this whole middleware thing. It's a lot of arm waving for a lot of years, and suddenly there's no more arm waving because you can have results. Like there's no hiding behind arm waving. So with Microsoft and also with other partners, we've looked very carefully at exactly what we can do with X number of qubits at Y rate. So that's now suddenly become real. And then I would finish back with BMW. I think that both the hydrogen fuel cells as well as battery storage and lithium ion sort of technologies, anything that moves the needle there is going to be important. I should mention, of course, that we now have, and this is answering your question as well, we've got about 30 million users of Ticket all over the world, which is our open access software development kit. And now that we've got these machines, we can start mining this incredible, I mean, its multiplicity is bigger than anything else out there. And that 30 million will suddenly become 100 million before you know it, and that 100 will become 200 million. So we'll start mining that. And in the area that we're working with Robert specifically, I think we're looking forward to figuring out how we can have this hybridicity so that it's not just a concept of having a high-performance supercompute, maybe even a generative cluster together with a computer. So what we've committed to our partner is that we're going to have a code LLM, which is plugged into our quantum computer. That is actually, if you want to really go down a rabbit hole, that's a big, big rabbit hole, because that extracts information that humanity cannot access at the moment, and then using that for the benefit of our partner so that we can cut corners in a meaningful manner.
It's such a great sign that we basically don't have time to go into all of the exciting possibilities here because the rate of progress is so quick. We are actually over time, but I just wanted, Robert, you to have the last word here. Many people in this room will be asking themselves, what does all this mean for the industrialization of quantum more generally? What would you say? What does this tell us about where things are going?
Well, I think there are really three ingredients we need to be successful. One is hardware, and we just heard you moved the milestones forward by years, right? So now we can effectively also develop the software stack that's needed, like error correction, right? And third, it's the teams who implement the solutions, because you need quantum experts, but you also need domain experts, like in quantum chemistry or aerodynamics, who know how to cut corners on classical computers. And bringing that together, that will make success. And we are having tremendous progress in the last year in technical aspects, as discussed. We are building teams, and we do have support of governments and private investment. So I think the glass is pretty full.
Excellent. Well, that's a lovely note to end on. Thank you very much indeed to Ilyas Khan and Robert Ruckman.
Thank you.